Welcome to the first video of the module on DC to AC power inversion. This is one module of the ENFUSE project that focuses on the integrated learning of circuits and systems concepts under the theme, in this case, of energy and environment. The topic of this module is the conversion of DC, or direct current power, to AC, or alternating current power. The labels DC and AC are a bit misleading. First, DC means constant or fixed current. So if I plot a DC current or voltage as a function of time, it will be a constant or fixed value. On the other hand, alternating current means sinusoidally varying current. So I will draw that as well on here. And you can see that it varies with time. The power provided by a wall socket is AC, while the power provided by a battery is DC. In most of the world, the duration of each AC cycle, and here is one cycle, is 16.7 milliseconds. This means that a frequency of 60 hertz, or 60 of these cycles per second. Now, why do we need to convert DC to AC? One of the most compelling reasons today is that photovoltaic solar cells provide DC, but the power grid uses AC transmission. So if we want to connect solar power to the grid, we must perform the conversion. Now, one of the questions that might come up is, why is the grid AC and not DC? It turns out there was a great competition about that choice, and you can Google a phrase called the war of currents. And I won't spend any more time on this except to say one more thing, and that is the key point about the advantage of AC is that AC can use transformers to boost voltage and therefore reduce the loss in electrical transmission lines, but transformers don't work with DC. As part of the ENFUSE learning approach, we will discuss both circuits and systems concepts. As far as the circuits concepts are concerned, we'll be covering some of the things you're familiar with, like resistors and capacitors, but we will also be covering other new devices that you may not have seen before. And these are nonlinear devices. One of them is the diode, which has this symbol, and another is a transistor. And in this case, we'll talk about something called a field effect transistor, and it looks something like this in terms of a schematic. So we have a diode here and a field effect transistor, or FET, here. We'll spend a lot of time also talking about bridge circuits. And bridge circuits are one form of circuit topology or structure that's very, very useful. And the idea is that something of interest, often a load, is placed between two parallel circuit branches. And finally, to control the bridge circuit, we will also talk a little bit about some digital logic, and in particular we'll talk about something called a flip-flop. In this module, we'll also discuss some important systems concepts. And perhaps the most important one is that we have to design a system that allows us to control the flow of electrical power. And one of the most important considerations of any system that would do this is energy efficiency, because we don't want to lose energy in the process of converting DC to AC. We'll also talk about two other broader systems concepts, And one is the implementation of systems using circuits and electronic components, and the other is the decomposition of a system into subsystems. And we'll talk about those a little bit more in detail in the next two slides. How do we approach engineering a system? Well, we start out with a needed function that needs to be performed. And ultimately, what we end up with is a system to perform that function. And in between then is the role of design. So we can think of design as this very important process that maps a desired function to a system that accomplishes that function. How do we implement a particular system? Well, if the system has to either process or move information about or move power about, it's probably going to involve electrical concepts. And we implement those concepts in circuits. So let's think about this. Suppose we have some system, and how do we start the design process? Well, one of the things we might do is break that system down into subsystems. Here we'll call them S1, S2, and S3. And we'll break the system down into subsystems based on functionality that must be accomplished by the system. So we'll take the overall system function, in other words, what this system must accomplish, and break it into subsystems that can do subfunctions. Then we have to worry about how to implement each subsystem. And it's very likely that we will implement a subsystem using a circuit. Or we may also, and in the particular case of our DC to AC inverter design, we might use a pre-built component. And that's what I'm suggesting here with this C1. Here is our DC-AC inverter described as a system. Now that system has an input, which is an energy source, and that energy source provides DC power. Our inverter system here also has an output. It generates AC power to a load. And a load is simply a term for something that dissipates power, hopefully doing something useful. And a good example might be a motor that's running a compressor in an air conditioner. Now, in our particular system that we're talking about here, which is a DC to AC inverter, we have taken this system and divided it into three subsystems. A clock source, here, a control subsystem, and an H-bridge. Now the clock source provides a clock waveform to the control system, that's here, and then the control system provides control signals to what's called the H-bridge. And if you remember, I referred earlier to bridge circuits. So the H-bridge is a particular type of bridge circuit, and it needs control signals to operate correctly. And we'll spend a lot of time talking about designing bridge circuits, and in particular H-bridge circuits, and a little bit of time also talking about how to control these circuits. Here's the structure of this ENFUSE module. You will have 7 videos, including this one, that talk about converting power from DC to AC. And I'll mention here that this system that does that function is called an inverter. And it sounds unusual because you might want to call it a converter, but it's referred to as an inverter for historical reasons. The bottom line is that in this module, we will develop the systems and circuits concepts needed to understand, design, and build a DC to AC inverter. After the videos, there will be a short example problem on energy efficiency, and then you'll have the opportunity to actually go into the laboratory and do an experiment where you construct and look at the waveforms generated by a DC to AC inverter. Here we show the 7 videos for this ENFUSE learning module. And we're at the conclusion of part 1, the introduction and motivation. And in the next module, we will go over bridge circuits.